Hello everyone, we are back again after the break. So, what we are studying the application in thermal and cold plasmas, and we are reviewing the key concepts that we have covered in the last 3 weeks. So, we are here, we are trying to understand the application of thermal plasma for material testing under extreme conditions. So, this is a unique application of thermal plasma jets for material qualification, which are intended to be used in fusion reactors. So, you all are familiar with tokamak device, where this fusion reaction is getting attempted using magnetic confinement. So, this is a torus within which the plasma will be generated, and what you are seeing, this is the diverter region, this is the first wall material which is surrounding this region. Now we are talking about millions of degree Kelvin which will be there in the core of the plasma for fusion to happen. Now, no material can withstand such high temperature. So, there are ways, there are detailed engineering to protect these first wall material or the diverter region material. But this plasma is prone to instabilities, and it may happen that this first wall material or material in the diverter region, they get exposed to unexpected heat flux or particle flux. Then what will happen to the material that is used for the construction of this enclosure? So, high heat and particle loads that lead to erosion by the plasma as well as high temperature thermal cycling, which can affect the mechanical properties and lead to fatigue for the material. Then deuterium and tritium uptake or retention, which adversely affect closure of the fuel cycle and increases radiation safety risk. Degradation effects by helium, which are typically destructive to materials when implanted in the near PFM surface. PFM is plasma facing material surface by the plasma, or formed deeper by neutron reaction. So, these are the degradation effects by helium. Now, neutron irradiation leading to material damage by atomic displacement and nuclear reactions within the plasma facing material. Synergistic effects, whereby high heat flux, high particle loads, out of equilibrium deuterium, tritium and helium concentration, the effects of thermal transients and neutrons combine in unexpected ways to produce changes in material properties and behavior that are outside the intended design limits. So, all these things can happen with the plasma facing material, and we need to develop material which can withstand such situation in a best possible manner. So, for that we need to generate first the kind of scenario that will happen in a fusion reactor. But unfortunately, for that you need to operate the fusion device, and each time you need to get the material extracted from there to understand what change happened to that material. So, that is rather difficult, because making and breaking a fusion device is very much taxing as far as manpower, time and money is concerned. So, there is an easy alternative. This one, where we have generated a thermal plasma beam as you are seeing over here, this is a helium beam which is coming out from the plasma jet, and as you can see, it is coming out like a laser beam without any divergence. So this is highly collimated long laminar plasma beam that is generated using this plasma device. This can give you the particle flux and heat flux which is comparable to the situation that will happen in the fusion devices. So instead of making and breaking a fusion device, we can use this kind of plasma beam to test the material whether it will perform as per our intended design specification or not. So this kind of plasma jet, plasma beam can be used for material testing under extreme conditions. Now this is another plasma application, plasma specific coating development. This type of coating, used for thermal barrier application and environmental protection of the material. One example I will give you, for suppose you are trying to make an aircraft which will be having very low thermal radiation. So what if that is there, then it will be difficult to detect that aeroplane by imaging mechanism, using thermal imaging mechanism, because it is not emitting that strong. So this kind of application will require coating of the surface with some material which will reduce the infrared emission. So for that you may need to coat certain special material over the surface, and one of the method to deposit such coating is the thermal spray coating. So apart from that, suppose you are going for this application where the surface is going to encounter a very corrosive environment. So some protective coating you can apply over the surface so that the original material doesn't get exposed to that corrosive environment. So these are environmental barrier coating. Now nowadays, this yttrium oxide, they are ceramics, they are having very high melting point. So those materials are getting coated using this plasma. So what is the advantage? This advantage is that because of the high melting point of these ceramic materials, they cannot be they cannot be brought to molten state easily for coating purpose. So plasma, because it is having very high temperature, it can melt those materials and make coating easily over the surface which is of interest. So here what you are seeing, we are using some powder feeder, and therefrom we are inserting the powder that has to be coated into the plasma jet, and that is getting molten in flight and getting deposited over the surface which is of interest to our application. So atmospheric pressure plasma spray coating, so usually they are called APS coatings. They are used in many areas like aerospace, biomedical, energy sectors, automotive industries, electronics. So the benefit that you get is good bond strength, high temperature resistance, wear and corrosion protection, customizable coating thickness and composition. So coating materials which are usually used, they include ceramics like aluminum oxide or yttrium stabilized zirconia, metals and alloys, then carbides, and then binder and particle size. They are of importance in this coating material, because to match the thermal expansion coefficient, sometimes you need to deposit some interlayer before you go for the final coating. So these are the atmospheric pressure plasma spray coating which you use for environmental barrier and thermal barrier applications. Now in plasma metallurgy, this plasma can do one step reduction of highly hazardous material, like here one example is given, that is the sludges which are coming from the common effluent treatment plants. So these sludges, when they are treated using the plasma, not only the organic component is getting out and this hazardous material is becoming benign, they are able to extract the material that is within there very easily. Here you are seeing that we have used three types of sludge. One is your polymeric, flocculant sludge, decanter sludge and spray dryer sludge here, and each of them you are seeing here that the plasma is finally able to segregate the materials. So these are usually the heavy metallic part and these are some inorganic parts, and you see that here they are getting separated so easily. So post processing becomes very easy. Not only that, what you are able to get, you are able to extract valuables from this sludge which was otherwise hazardous to the human being. Now here we are going for plasma application in the plasma medicine area. The emerging non-thermal plasma technology in the medical sector. Here cold atmospheric pressure plasma is used that works at near room temperature. It is minimally invasive and non-toxic. Then it gives you reactive oxygen and nitrogen species, induces apoptosis in cancer cells, disrupts microbial membranes, stimulates tissue regeneration. It works for wound healing, sterilization and disinfection. For cancer therapy, it has shown very promising results. It works fantastic for skin diseases like psoriasis, eczema, and it is nowadays effectively being used in the dental treatments. So it offers actually selective cytotoxicity against tumor cells. So it kills the carcinogenic it kills the cancer cells but doesn't do anything with the healthy cells. The fact is that it induces stress to both the healthy cells and the cancerous cells, but because of the higher metabolic rate in the cancerous cells, it divides very fast. Already the stress level is more in those cells. Now if you apply some external stress over the cells, then for the cancer cell it goes beyond the death limit. So those cells dies, but for healthy cells this increases but remains within the bearable limit. So after you have removed the exposure to the reactive plasma species, then what happens, this healthy cells recover but the cancer cells dies permanently. So this is the simple technique by which apparently the cold plasma is working on selective killing of the cancer cells. So it induces oxidative states, promotes immune response against tumor, accelerates healing of chronic wounds, promotes angiogenesis and cell proliferation, reduces microbial load. So angiogenesis is basically you are growing more this this veins kind of thing in the tissues for healthy environment for the circulation of bloods and others. So it can easily reduce the microbial load. So plasma, the cold plasma application is helping in a significant way in the biomedical areas. Now, this is one in our lab which is showing the plasma jet that is discharging on some liquid, and it has been compared with the radioactive sources which emits alpha, beta, and gamma. So alpha is nothing but the helium nuclei, then gamma is the electromagnetic wave, and beta they are the electrons, right? So when you are generating say helium discharge, you can easily produce this helium nucleus, electrons, and the electromagnetic radiations. The helium ions, they are nothing but these alpha particles, and electromagnetic waves, a range of electromagnetic waves can be generated from the plasma depending on the kind of medium that you are getting that you are using there. And then plasma means lots of electrons, so they are nothing but the beta particles. Here what the issue is that this cobalt 60, for example, they are emitting the gamma at specific energy values, and they are in the very high energy in the MeV range. But in our plasma, we can control the energy of the alpha particle that is getting used, that is getting generated from the plasma. Similarly, we can control the energy of the electrons as well, and of course changing media, we can change the electromagnetic waves, but they all are not in the range of MeV, not even in the keV. So they are in the EV range. So the method, mechanism, and effectiveness will be definitely vary, but we are able to produce similar this nuclei in cold plasma as they are in the nuclear radiation. Only the energy ranges are different, and the way they works on different applications I have already told you. So here is one example where this effectiveness study in breast cancer cells is presented. Here this initial colony is there, then untreated cells after 48 hours, then cells treated with argon plus nitrogen for 10 minutes, and then after 48 hours it has been taken, then cells treated with argon plus nitrogen in atmospheric pressure plasma for 10 minutes, and then after 40 hours, 8 hours, what you are seeing. So you can see that these are the replicate 1 and replicate. In both the cases you are seeing that this cold plasma, atmospheric pressure plasma jet of argon and bit of nitrogen, they are able to clear all the cancer cells so effectively. Now coming to the plasma agriculture, I will be talking about the synthesis of plasma fertilizers. Nitrogen fertilizer is one of the common fertilizer that is used by farmers in the form of urea, CH2CO, NH2CO, NH2, that is the chemical formula. But surprisingly, you see that our environment is full of nitrogen. Then why the plants cannot take the nitrogen from the atmosphere? The reason is that this N is having a triple bond which is extremely difficult to break. So something is required which will break the nitrogen triple bond and give nitrogen atom to the plants. So and that is usually not possible ordinarily. So plant cannot consume the nitrogen from the atmosphere and use it. There are certain microbes which can break this bond and give it to the plants. They are called nitrifying bacteria. So even though we do have enough nitrogen in the atmosphere, we cannot use them for the agricultural applications. But nature has a method that is called lightning, where because of the very high temperature arc that is generated in the this lightning, they can break the nitrogen bond, and once the nitrogen bond is broken, then this nitrogen atom reacts with oxygen that is available in the atmosphere, then they form this nitric oxide, then nitric oxide reacts further with oxygen, they form NO2, then this NO2 reacts with the uh, moisture that is available in the cloud, then they form this nitric acid, HNO3. And this comes down to the ground, and plants absorb that, then that's how they get the nitrate through natural mechanism from lighting. So, the nitrogen cycle you already know from your school level syllabus that there are nitrification and denitrification. There are nitrifying bacteria, denitrifying bacteria. So, nitrifying bacteria helps them to assimilate the nitrate through the roots, whereas the denitrifying bacteria releases the nitrate in the form of nitrogen to the atmosphere. So, this cycle continues and the plants survive. Now, when we are using commercial fertilizers, so they are using ammonium nitrate and calcium nitrates. So, they are giving, when you are giving ammonium nitrate, they are giving ammonia. So, one nitrogen is there, and ammonium ion, one nitrogen atom is there, and nitrate, another nitrogen atom is there. So, nitrifying bacteria, what it is doing, it is taking the ammonium ion and converting that into nitrate, and that nitrate plants is absorbing. Then the other nitrate, which is already in the form of nitrate there in the ammonium nitrate, they are getting directly absorbed. So, one part is coming through the bacteria, another part is coming through direct nitrate. Now, this is the way the this NH2CO NH2, the urea usage is done in agricultural sector. Now, the problem is that depending on your pH level and the temperature, it may happen that ammonium ion will form ammonia gas and go into the atmosphere, or it may happen that ammonium ion is coming to the bacteria and forming the nitrate, depending on the pH and the temperature. So, it has been estimated that a small fraction of the total urea that has been applied to the field ultimately reaches to the plants. Here, when you are forming the this nitrate, it is called Haber-Bosch process, and this produces tremendous amount of CO2. So, you can see here that it generates around 1.9 tons of CO2 per ton of ammonia production, and it occurs at very high temperature, very high pressure. So, it is around 450 degrees centigrade, 300 bars, and it accounts for 1% of global annual CO2 emission. It consumes similar 1% of the world's total energy supply. So, the search is there to get zero carbon emission nitrogen fixation process, green and sustainable industrial chemistry. So, for that, this one plasma technology has come in a big way. So, the issues with the Haber-Bosch process are listed here. It is not decentralizable, cannot operate with intermittently available renewable energy sources, uses fossil derived fuels as source of hydrogen and hence not sustainable, has significant impact on economy as it involves cost for transportation of raw material and distribution of product. Ammonia storage requires high pressure at ambient temperature or minus 33 degrees centigrade under atmospheric pressure. So, here comes the plasma nitrogen fixation. Plasma induces excitation, vibration, dissociation, oxidation and reduction of nitrogen and dissociation of nitrogen fixation products at the plasma liquid interface. Then plasma allows direct interaction of water and nitrogen and fixed nitrogen. Then depending on the type of plasma catalytic system, plasma can instantly fix nitrogen in the form of nitrite and nitrate. And in presence of catalyst, plasma catalysis may enhance the fixation rate manifold, a highly active area of research at present. So, this is the way it works, and here we have seen one device that we have developed in our lab. So, nitrogen and oxygen enters into the plasma device, they get broken into atomic nitrogen, atomic oxygen, then the this water mist comes, the plasma enters into that. In presence of catalyst, it forms nitrate and nitrite, and that goes into the tank. So this is the tank, and this process continues on and on. In around 20 minutes, it gives nitrate, which can be suitable for one-time application in 1 acre of land, and the effort is there to reduce the cost of application and the energy consumption. So this is the way. Some distinctive feature of this application is that a single step process in thermal plasma, air plus water just gives the nitrogen fertilizer. Such process is equivalent to continuous lightning process under optimized condition, giving synthesis rate several orders of magnitude higher than that achievable in competing non-thermal plasma process. So the synthesis rate is manifold higher, rather many orders of magnitude higher compared to that is available in non-thermal plasma process. No vacuum or high pressure required, works at atmospheric pressure, doesn't use any fossil derived chemical, directly converts freely available abundant atmospheric air into nitrate and nitrite through interaction with water in a very efficient and low cost controlled catalytic plasma environment. And it completely avoids production of greenhouse gases like CO2 if run with renewable energy. So this is highly portable system, can operate with intermittently available renewable energy sources. So easily offers reactant density at least 5 orders of magnitude higher compared to non-thermal plasma. The system offers a clean, sustainable, decentralized, flexible system for fast synthesis of nitrates and nitrites. It can meet on-site crop demand in requisite amount as and when required. It avoids safety hazards and cost related to requirement of continuous energy sources, pressurized environment for synthesis, regulated storage, refrigeration need, transport of raw materials and distribution of fertilizer. So this one is shown here is the application. This is a control where no fertilizer is given, and this is one where this plasma fertilizer has been given. You can see the this is a corn crops. So you can see the corns that has been grown over here, but here nothing is there. So effectiveness is clearly visible. Now in case of noble material synthesis, this plasma can be used because of the very high temperature. What happens, you can break the material into its constituents, and then as it goes down, goes through a gradient in temperature, then they undergoes homogeneous nucleation. So through that the particle starts growing, and there is a critical temperature below which the growth of the particle stops, and usually that stops at a nanometer level. So that is a very useful top down and then bottom up approach to synthesis the nanomaterials using thermal plasma. Here you are seeing this is the neodymium oxide, and these are the nanoparticles that has been formed using the radio frequency produced plasma. So you insert the micron size particles over here, they get evaporated, atomized, ionized, and as they goes downstream, they come across a very huge gradient in temperature, and they nucleate, and finally they forms the nanoparticles over here. So this is a very useful application for synthesis of nanostructures of almost any material that you can think of. So this can be used for novel material synthesis like air through ceramic route, and here you are seeing that we are able to achieve that very nicely. So this much here. So we have reviewed the most of the basic concepts that we have covered in our regular classes, and I hope that this course will be very useful to you and will encourage you to go for newer and newer application in the coming days. You can contact me in case of any doubt anytime in future. So thank you very much for attending the course, and all the best to all of you. Thank you very much.